Hey everybody, you who have managed to drop in from the lobby. We'll get going with this webinar in just a minute or two, I think. We'll let people who have tech issues saunter in at their own pace. I think we'll get going in 60 seconds, something like that. Right, so how about I just start talking as some sort of sound check so people can get their gear up and working. And when stuff actually works, Ola and Andreas can start talking with the interesting stuff. Hey everybody, welcome to the first Bigpicture webinar of a long series that will mostly detail progress in the project to share the good word about all the good and cool stuff that we will be doing in this project. I'm Joel Hedlund. I am normally the data director to CMIV and IDA, working out of Linköping University in Sweden. And I'm also heading up the IDA Data Hub, which is sort of the same thing as Bigpicture, but only for Sweden, but also for radiology. So in Bigpicture, I'm the Work Package 2 lead, where we are building a repository infrastructure for European digital pathology AI. And I'm doing that together with my friends at the CSC in Finland and Uppsala University in Sweden. And now there's a horrible amount of noise. Can I ask everybody to mute if you're not muted already? Thank you. That's much better. Yes, where was I? Uppsala University. Yes, we have with us today a few of my friends from Uppsala University, Ola and Andreas. And I am really excited to hear them talk about federated machine learning. I've been following the careers of Ola and Andreas with excitement, actually, because it seems like they're always up to some amazing stuff, some mind-blowing stuff in robot labs and high content screening and stuff like that. So let's see here. Ola and Andreas, professors at Uppsala University, are usually doing the kind of stuff that I just said. They've also spun off a company called Scale-Out, and the company Scale-Out has made a number of very appreciated workshops on federated machine learning. And Ola, back in spring, offered to do something similar within Bigpicture. So we said yes, and we found a format that could possibly fit for Bigpicture, and here we are. Yes, how many people do we have here today? 40-ish so far. I'll go on for a little bit more. Why do we like federated machine learning then? Well, in Work Package 2, we aim to enable a federated storage and compute solution for a lot of data that's sometimes hard to move. And then it's quite nice to be able to compute where the data is and then combine output into something final that is then publishable or representative of the entire data lake, if you want. So this is like artificial intelligence, but with more problems, and it's kind of a holy grail, which everyone wants to do, but we will do it. And the attentive of you probably know that Bigpicture has some tasks and deliverables on federated machine learning that are led by Oken. Let's see if do we have some Oken people here? Charlotte, Marina, Camille, Matthew?
I'm here actually. This is Victor.
Hey, great. Hey. Oh, cool. So they will lead a task. Which task is it? I forgot, sorry. 414, maybe 412. It starts in month 24 anyway, and there's a deliverable as well at month 36 on deploying Open Connect in the Bigpicture repository infrastructure. But if you're interested in machine learning, I'm sure that Oken will be really very happy to get in contact with you and start discussions already now. There's some housekeeping to go through. This meeting will be recorded and shared on SharePoint internally in Bigpicture. And as I said before, you're very welcome to turn off your mic when you're not speaking, but you can turn on your camera if you want. That's more sociable. You can unmute yourself when you are asking a question, of course. There's also a little hand icon that you can click, and then maybe I will see that you're waving your hand and I can let you ask your question or chime into the discussion. Yes, I think that's it. And if people still have tech issues, then I can't help you, I'm sorry. I think it's now time to go over to the interesting part of this webinar, where Ola and Andreas kick this off and explain federated learning to us.
Yes, so thank you very much. Let me just see if I can get this up full screen. Does this look okay? It looks okay on my screen.
It does.
It says to me, people are waiting in the lobby. I guess I'm gonna hand that over to others. So thank you very much, Joel, and Rick for inviting us and for the kind introduction. So my name is Ola Spjuth. So I'm a daytime professor at Uppsala University in pharmaceutical bioinformatics. And let's see if I can change the slides. So I will today give a presentation with my colleague and good friend Andreas Hellander. So we are both at Uppsala University and leading our research groups. I'm also the AI coordinator at SciLife Lab Data Center, and this is a rather large endeavor in Sweden where we're collecting a lot of the molecular and life science infrastructure and research. Andreas is also the director of Essence, which is the e-science center in northern Sweden. And as you all mentioned, we also have a spin-off company, Scale Out. We some extra work. Andreas will get back to that later. So I'm just going to say one slide about my general research, what I'm not going to talk about today. This is my research on AI machine learning, lab automation, and cell profiling. We work generally with high content imaging and with multiplex dyes on large scale, the cell painting methodology. And we have built an open source, fully automated cell profiling lab. And this is where we get our large scale data resources, which we then, and I've worked in many infrastructures and European infrastructure projects also, and the IHPC center here. So we're good at computational data management infrastructure for continuous AI modeling on these types. So we are really targeting the mix of AI robotics with experimentation and try to work towards more autonomous experimentation. Here's the GitHub link if you're interested in all of this. Of course, everything we do is open source. But today, I'm not going to talk about that. I'm going to talk about data and the challenges with data and modeling. And I think I'm preaching to the choir when I show this slide, in a sense. But I think this is going to be something that divides the people with access to data and those without. So the big tech companies right now that have a lot of data are investing a lot in AI and machine learning. They really gain a competitive advantage. And this division between these companies that have access to these data sources and the others that do not, that sort of the gap grows bigger as we go. But the problem for many is that a lot of data is isolated. I mean, it could be because we don't want to share it. It might be private, proprietary, or as probably most relevant for this crowd, regulated. Are we allowed to share, such as health data, sensitive data, and so on. But also they cannot share, for example, if you have very large data sets or the networks are unreliable and so on. Well, there are practical blockers for why you cannot do this. So the effect is, of course, that a lot of data that would be valuable to use is not available. But we might still want to do these data collaborations. There are a lot of gains that can be made. I mean, for example, we could test the best possible, try to train the best possible model if we collaborate, or we might maybe want to solve a common problem. So I worked with pharmaceutical organizations, pharmaceutical companies that, for example, even though they try to develop drugs towards different types of diseases or areas, well, they all share in, for example, in small molecule research, they all need to deal with safety modeling, toxicity, and these general things that it would be really nice if they could pool resources and solve those common problems. But it's very challenging to have pharmaceutical companies share data with each other. It's like, I worked a lot with that without much success, I have to say. So the term privacy preserving data analysis is well, kind of obvious. That can we then enable sharing this personal data without compromising privacy? And we might want to sort of find secure ways of providing public access to private data sets. How can we do that in a good way? Maybe we want to do joint analysis on private data by several organizations, which we will touch upon today a bit. Maybe we want to securely outsource computations on private data, or decentralized services that rely on private data from individuals. So in the life sciences, Data Shield has been around for quite many years now, and they have tried to work on this privacy preservation area to sort of enable analysis of individual level data, but sort of without, so that they add on a package to the clients participating in sort of a constellation, so that you can co-analyze data at different sites, but you have a sort of a broker that makes sure that you only share or disclose information that is sort of so that is non-disclosive. So, for example, you have sufficient summary statistics and aggregated levels, and this has been rather successful. But it's really been a clear focus on epidemiology. And we talk here today about digital pathology and AI machine learning, and I think we are all convinced in this crowd also that neural networks and convolutional neural networks, they have been demonstrated to work well in many cases. And I think that you will also agree with me that a key problem to get good models is access to sufficient high quality annotated data. And this is a challenge. I mean, could we, for example, access to samples, annotations, collections, curations of these data sets? And we know that in order to train generalizable models, well, we need sufficient data heterogeneity in this sense. What can be done? Can we collect all data in one location? Well, I think that is going to be problematic due to the sheer size of data, but also regulations. I mean, in the short term, well, this is probably not going to work out. In the longer term, I think it will definitely be very difficult to work out. So can we build large public high quality reference data sets? Well, that would be good. I agree. Can we get them to be large enough so that they would solve the data problem? Unlikely, I think. So can we train a new model for example, for each point of care, each hospital? Can we train a model on their data? Well, yes, we can. Will this model be as good as if we had more access to all data? Very unlikely. And this will also mean that you will have different models at each different hospitals with different performance and so on. Can we train a base model and then calibrate it per deployment? So in a transfer learning way? Well, yeah, we probably can. And I think that these two last points here, training a new model or training or calibrating one per deployment, is probably where most efforts are placed today. But that's a bit more what I am guessing in this sense. But wouldn't it be nice to be able to train a model from while keeping the data at the sites, but then train a model from it jointly? That would be really nice. So maybe the simplest way of doing this would be to just combine predictions. This is my own humble contribution to this field. We did a few years back. Instead of pooling data here in the center, I hope you can see my pointer here. Instead, we train model on each party sites, and we have different types of data sources, and then we just aggregate the results back, and then we have a query, and we get some sort of prediction. And
sorry, Ola.
Yeah.
I don't think I can see the pointer. If that was important.
No, it's not important, but let's do
fine.
it this way. I think now you
Great.
hope
now I can.
So instead, you would send the query back to the different parties, and then you have some sort of train model you can then aggregate. In this case, we did a study for prediction intervals and so on. So that would be the simplest thing to do that, but it's sort of it has, of course, obvious drawbacks. Well, I mean, you still train individual models, and you just aggregate the intervals at the end. So this talk is really about federated machine learning, and here you want to train a global model. So multiple parties contribute to this without disclosing data. And if you have an aggregation server, like the yellow here in the middle, you would send out the model to the local parties. They would train with their local data, send some sort of incremental updates local to the server that can then be aggregated of. And the actual information and data transferred over wires cannot then be traced back. I mean, in the best of worlds, to any, so that you don't disclose any of the training data. And after repeating this process many times, we can sort of we obtain a good model that's trained on the data on the local sites, but we have not shared any data between the parties. You can also do this peer-to-peer without this central aggregation point, but then instead you synchronize models, you train locally, and then you just exchange the models with each other, and you do aggregation at all sites. So you remove the obstacle of having a central coordination, but you add more sort of logic to the different parties participating in these things. When you can repeat them. So this is more the peer-to-peer. So these are the two most basic setups for federated machine learning. So it has the concept of federated learning has been around for quite some time, but I think it got a really big boost from this blog post by Google in 2017, where Google showed how they trained federated models based on the cell phones, where on each cell phone there would be some local improvements in the learning that was then shared with incremental updates and then that would then build iteratively using sort of encryption, then contribute to training global models that was stored then in the cloud. And when we then go in federated learning and digital pathology, well, it sort of course, we see some obvious additional challenges, and what you said, sort of AI with more problems. And yes, there are challenges, of course, to this. When we have data in multiple sites, it's kind of obvious that the sample distribution will be different. The sample prep might not be the same. You might not do the same type of staining, for example, or use the same equipment or microscopes. Maybe the protocols are different, and the people doing annotation and so on. There are a lot of challenges of this. But also for the actual learning, there are more issues with security, privacy. How can you then validate these types of models and have confidence in your predictions? And how do you treat misbehaving parties and so on? Andreas will touch a bit more upon these parts also in the later part of his presentation. But before I let Andreas take over and say some more on federated learning, I'm going to give some recent examples of some success stories of what people have published. So this is a relatively recent bioRxiv paper where the authors trained the model to segment interstitial fibrosis and tubular atrophy, so IFTA. And you can see here also they have a very similar, like the aggregation server, that they trained a local model on local data on different nodes, and they have a central server where they sort of average over incremental parameters and train then a global model. So they showed that they had in this case 4 institutions. So these are 1, 2, and 3, and you can see that this is a ROC curve, that they get an improvement, of course, with the orange where they pool everything centralized, but they reach almost the same performance with the federated. So this was with a holdout, but in this case, to the right-hand side, they had a 4th institution that they then used as a test set to predict it on. And then they observed also that the federated model actually had higher performance than the central instance. But in all cases, using a federated approach improved over the different institutions if the model were trained on the individual institutions' data. Here's another slide. Here's another recent presentation where they tried to look at the federated learning for style normalization from stains, and then they trained a generative adversarial network, a GAN, where they have different clients with different types of data, having different types of stains, and they train local discriminators, and then which are then merged into a global generator, and they would sort of do this in a federated learning session, and show that using this federated approach, they could achieve here on the right-hand side a better normalization according to their efficiency criteria. So it shows the application of it more than I will say that this is the state of the art in a sense. But in their study, they compared it with other methods for style normalization that people used, and showed that this improved. This was spurred quite some noise when it appeared, I think, in 2020, where they had federated learning on MRI images. The task was to distinguish healthy brain tissue from tissue affected by cancer cells. And what I liked about this study was that they actually had around 10 institutions to participate in this research, and they showed that they reached 99% of the model quality compared to centralizing all the data in one position. And so that was a good showcase of working with these types of the images in a federated manner. And my last example is this, which was also from 2021, where they did this. This one did a more peer-to-peer version, where they combined federated learning with peer-to-peer, and they also used blockchain on these peer-to-peers, and they referred to it as swarm learning here, and they used this to predict leukemia from blood transcriptomes, and also tuberculosis and lung pathologies from X-ray images. And also here they showed that this type of federated learning outperforms the models at the individual sites, and they sort of, well, this was published in Nature now in 2021. So there are a lot of examples of emerging now on federated learning, and it's sort of, if we just say that AI in pathology has high potential, yes, there remains many challenges to overcome to have this, of course, to get this into clinical practice and so on. But I believe that federated learning is a promising avenue to overcome at least many of these is related to data access. But sure, it adds other challenges that you need to consider, and that's why we need more research in this field. We need more data sets so that we can do research on federated machine learning. But one thing that complicates matter is that doing research on FedML in live settings, well, it sort of necessitates that you work with multiple institutions, and these collaborations and these projects are usually more difficult to set up in order to do that. And without the lack of proper data sets to do research, it's also difficult to do research outside of these types of cohorts of collaborations. Sorry. And with that, I will hand over to Andreas to continue talking about a little bit more on technical on federated machine learning. Andreas, over to you.
Thank you, Ola. I hope everyone can hear me and see me and my slides. Yes, good.
You can see your lower half of your beard.
All right, I will do it like this now. Yeah, so like Ola said, I plan then to give a little bit of a perspective from the computational side, a little bit talk about what are the challenges, the main challenges that we see from a computational perspective, and also a little bit about our work in our lab that we do together with Ola, also how we can address some of these challenges. So if we just reiterate what Ola said, I mean, the promise of federated learning, you can think about this in many ways. But in the picture to the right there, you see a convergence graph. So this is a CNN that is trained for classifying acute myeloid leukemia cells into different stages. This is based on a research data set that was published quite recently. And the graph you see there in the blue curve is when we took this data set and we partitioned this in 10 different sites, mimicking 10 different clinics. And you can see that they sort of represent the best model we were able to train on the data from a single clinic. And then the orange curve is the model we were able to train when we centralized all the data. So we trained, this is the normal machine learning on the pool data. And then the green curve is then the federated averaging, which is added sort of an algorithm in federated learning. So what you hope to achieve in this big promise is really like the ability to train something that is very close in performance to the hypothetical situation of a pooled model, and often then outperforming what any participant in such a federation could do on their own. Something that generalizes better. And the picture to the right there is like the sort of canonical picture of how this happens, that in the simple setting you have a server and then a bunch of clinics or clients, as we tend to call them in the federated learning literature. And they are then locally updating, and there is some aggregation happening, and this is iterated in different rounds. So this is kind of the alignment of what we are looking at with federated learning. And I just wanted to mention, I mean, there is of course mathematics behind this, and you can formulate these aggregation schemes and algorithms in math, and there are hyperparameters, as they are called in machine learning, that pops in up here that you can think about how to optimize and how they should be chosen. And there is a very big sort of research activity ongoing into how to construct such aggregation schemes to be good in different respects and handle different types of challenges. But a good first reference is this, by now, it's very young papers, it's hard to call it classical, but almost classical paper on federated averaging. And you can also analyze this mathematically in many situations and see and prove that things converge and so forth. So this is important computational aspects. But there are challenges, of course, and one of them Ola hinted at. And the first challenge I would like to highlight here is that of statistical heterogeneity. So typically what you would see is that you have unbalanced or non-IID partitions in a federation, or the data in the different silos are not IID. And you can also highlight and do experiments to showcase the effects that this can have on the convergence of the federated schemes. So the plot to the left here is also a convergence graph when we train, this is a benchmark problem, object detection model with Cypher-10 datasets. And what we did here is that we made pathological non-IID partitions where each partition might only have representations of certain or few of the classes in the data that we're trying to predict. And as you can see here, as you make this increasingly non-IID, you might end up in a situation where, first of all, convergence is affected, but also potentially the accuracy. So this is a challenge also that the research community is looking into, and there's different strategies that you could attempt to mitigate such issues, both on the algorithmic side and also by augmenting data. But there's also a reference there that you can look at to learn more about that. The second challenge I would like to highlight is that of system heterogeneity. Naturally, in federated learning, and this is often quite in contrast to centralized or traditional machine learning, is that all of these clients or sites can be expected then to have hardware of different quality, and they have different quality of the network connection. And this can lead, for example, to this problem we call the problem of stragglers, that what happens if some of these clinics are not able to update the model in a certain time. So they fall behind. Should you then let them update the model and participate in the aggregation late, or should you throw away that run's contribution? These choices, they have effects on the convergence and also the accuracy. So this is also a challenge that is being addressed in the research community on the computational side. And then the third one, which is close to heart for me myself, is that of scalability. So this picture that you often see is of course problematic in the situation where this kind of traditional client server implementation, it is nice. And it is the most common one if you look at research codes, maybe not production codes. But of course, if you have a very large number of clients, or that you have clients that send very large updates almost at the same time, this tends to overload or saturate the server. So it is a computational problem to make this scale beyond small settings, especially when models become large or when the clients become numerous. So the scalability challenge is also there. That is something very important. And where I'm getting with this is that it's important structurally when you look at this the problem. It looks like it's the distributed machine learning problem, which is about taking a parallelizing training. And you can do this in many different ways. It could be a data parallel strategy, which is kind of what you take in federated learning. You can also do model parallel strategies. But in that setting, you typically have full control over the data partition, and you often have more heterogeneous infrastructure. So the statistical heterogeneity and system heterogeneity are special to the federated setting, which also makes it a bit different on the algorithmic side, even though it of course has a lot of commonalities. Looking at federated learning from a privacy perspective, one can say that federated learning, what it does, the proposition there is that it addresses input privacy. So it protects the input data, the training data, by not in the simplest way possible, that you don't actually move it. So that if you're an organization, your data remains in the administrative control of your organization, and then you have whatever sort of measures and routine you have for data security can still be in play. It's when you read about federated learning, it's a field also where you typically mix this with many other areas of privacy preserving machine learning. And then if you think about the output privacy problem, where we look at, okay, given access to the model, how much can we learn about the input data that was actually used to train it? So that's the output privacy problem, and that's really not in itself addressed by federated learning, but it's typically then other techniques that are used in conjunction with it to improve the situation. So what you see is that federated learning is often constructed together with other of these techniques, like differential privacy, which is a way that you can add controlled noise to different parts of your computation to improve output privacy, or secure aggregation, multi-party computation, or even homomorphic encryption in some situations. But yeah, that's kind of quite limited still. But these are also ways to increase the security primarily on the output side. So a little bit about what we are doing. So I wanted to talk about this paper draft or preprint that we have up on archive. It's called Scalable Federated Machine Learning with FedN. So FedN is an open source framework for what we call hierarchical federated learning that we develop in our group and also then in scale out. So this is a collaboration between the spin-off and the lab. So if we recall the scalability challenge, this picture here, I mean, you can think of two possible ways to overcome the problem of scalability. So one of them is that you keep this kind of setting with a single server, and then you subsample clients in each round. So if you have too many clients, you don't include everyone in every round, just to sort of have enough that your server can accommodate it. And this is a viable strategy, and you can have client selection schemes and try to optimize how you should select them and so forth. But But in general, it is better for convergence to use as many clients as possible during updates. So the other solution, which is conceptually very simple, and this is the one that we are taking in our research, is that we simply add more servers. And it sounds very simple, but that, of course, the consequence is increased system complexity. And you can do this with a strategy called hierarchical federated learning. And this picture here shows this on a tiered form. So in FEDN, in our framework, we have essentially 3 logical layers. One we call the reducer layer, one we call the combiner layer, and this is the combiner network. And then we have clients, and these are the ones that are sitting on the data then, on the data silos. So this is what the deployment of FEDN consists of, is a network of combiners, one or many, that each have a delegated responsibility for a certain subgroup of clients in every round of federated training. So a flow in the computation could be that there is a controller that lays out the compute plan for the whole computation. It instructs the combiners to update, to compute partially updated models, and the combiner then goes and does that independently, coordinates that with their clients, and then gets a partial model update back. And then there is a final sort of global reducer protocol that combines the models from combiners into a global model. If you have a computational background, this model is nice because it looks very much like MapReduce, if that is something you have heard of. And what that means from a theoretical point of view is that we know that this architecture will be massively horizontally scalable. So we can accommodate a very large number of clients or large data volumes by scaling out the number of combiners in the network. So this is why we do it this way. But this picture here could be also more another perspective of this, and it also enables highly decentralized model training. And this is something that is important because we also work on what we call the cross-device situation, where, for example, autonomous vehicles are participating in federations to compute, to do federated models, where these combiner networks, combiners can be deployed in a network on edge data centers. So you can have also address latency issues when you have many clients. That is perhaps not the most relevant case in digital pathology, but it is a property of the solution. But of course, in the setting where you only have one combiner, what we have is that it reduces to the simple sort of federated averaging setting. So depending on how you deploy FEDN, so we move sort of from the architecture of the framework to the deployment level, we can accomplish very different situations or settings. And in this paper, then we explore this in different use cases. So one of them I wanted to highlight here is like a cross-silo situation where we look at the problem of, okay, what does the scalability look like when we make larger and larger model updates? So we have an NLP model here that ranges in size from, I think, 20 megabytes up to a gigabyte. And then we sort of stress test the network. We do it with 4 combiners, each sitting on virtual machines in different regions of the Amazon cloud. And in the end, we had 40 clients spread over 40 combiners, and every round involved like a network traffic of 40 gigabytes worth of model updates. And in this situation, we can achieve like a data flow at peak of about 450 megabytes per second on a 1 gigabyte line, which is very good. It means that the framework has very little overhead and can be scaled to very large deployments. So to recap, I wanted to summarize a bit of the R&D challenges that we see from the computational side that are exciting. And one of them, of course, is performance and scalability. How do we design algorithms and frameworks to work well for federated learning? Security, I mean, how we make the system robust to dishonest members and external threats. And then another very sort of interesting area of this is trust and decentralized computation. So you can go into that extreme end as well and look at how could you do federated learning even without any trusted parties. So this is also something that people are working on. We also do that a little bit on the side. Yes. And as Ola mentioned, I also promised to say a little bit about the spin-off that we have. So it's a startup. We're based in Sweden. We're based in Uppsala. So these are our 2 office locations. We are a remote first company. We're 6 founders and 4 or 5 full-time employees, 4 right now. So 10 in total in the team. We have offices in Uppsala and Stockholm. And we work with different companies. So this is a little bit of a timeline of how we have evolved. And I think it's also a nice way to see that federated learning is really gaining interest in many different sectors. We're heavily involved in a collaboration in Sweden called AI Sweden, where we work with companies such as Sensact to explore different use cases in primarily cross-device federated learning. We have also done, for example, a recent pilot study with the Royal National Library in Sweden, where we look at training language models in a federated setting with FedDAN. So this is a little bit of, I think, nice way to say that federated learning is also gaining ground in many different industries. We are in a big new project about air traffic management, for example. Yes, and then also Ola mentioned we have, so this talk is part of like a workshop that me and Ola does with a product that we are developing, FedDAN and Scaled Studio. And what we do here is this model that I showed you a bit about the how we classify blood cancer cells. We actually do that as an interactive sort of tutorial workshop where you get to participate in forming such a federation up to 20. I think we do 20 participants, and then every participant is supposed to set up like their own clinic or their own site. You get the data partition and you're configuring your own sort of local clients and you connect to this federation. So it's quite fun usually. And I thought, of course, we cannot do that now, but I will just quickly show you some sneak peeks of what it could look like. So here, I think you see this window, right? Yeah.
Yes.
So what we have here is Scaled Studio. It's a sort of integrated system we have built where you can go and deploy your models in production. So this is the model serving problem. So in this workshop, we first start by training the best model we can on the partition from one clinic or one site. Deploy that with TensorFlow serving, and then you can format. This becomes a silly little user interface. You then deploy in a studio where you can pick, a cell and you can do a classification. But then this model is not very good since it's trained on quite little data. So what we do after that is essentially go into these federated projects where we deploy a FedDAN network. We can look at the model a little bit. We can learn about to work in Jupyter Lab inside Studio and learn a little bit about how the model works and so forth. We prepare sort of the compute package because it's important to understand in the federation. I mean, there are, of course, in federated learning, a lot of plumbing that needs to happen. You need to prepare the code that is supposed to be executed on every site and things like that. And this is something we explore and how that can work in our solution. And then we go ahead and deploy these networks, which is the FedDAN system. And I have pre-made that here. So what you could do then is to connect your let me just reshare the screen in a second. So you see you need to see the whole window. So you end up essentially in the end connecting clients from maybe virtual machines or terminals like this. And then we can try to together improve the model via federated learning. And then sometimes if we are enough in the workshop, it succeeds, and sometimes not. But that is the sort of gist of it. So I think this is quite nice. You can see one of my clients started training here, and the other is waiting for instructions. So that's very good, all very good. Yes, so that is essentially what I wanted to say. And if you want to talk to me or any of the developers or Ola, we have a Discord server where we hang out and talk about decentralized AI in a quite general sense, but also, of course, about FedDAN and the solution stack in Studio that I just showed you. So that's all I had to say about federated learning today, and I hope we managed to give you some perspective on sort of why is this problem interesting from a computational perspective. Thank you.
Thank you. That was a great webinar. I'm feeling really inspired, and of course I, as always, have a truckload of questions, and I will pepper you with them. I'll let everyone else prepare themselves to ask their favorite questions, and in the meantime I will make a comment that you mentioned that one of the hardest things about this is to get enough different institutions to capture the variability in the type of data that you will encounter in the world when you have a product or something and expect to sell it on a market. Well, that's one thing that we're trying to address in Bigpicture. We're sort of doing the centralized thing because that's what was asked for in the call. So we're building a centralized repository where tens, hundreds, different data contributors will pool data from various parts of Europe, but we're also enabling setting up standalone silos, if you want, in federated repositories. This federated learning, we see that will probably be something that is extremely important and extremely valuable more and more as time goes by and as this digital revolution in pathology goes on in Europe and the world. That's enough out of me. I see Jeroen has his hands up. Can I get you to comment on that or anything else, Jeroen?
Yeah, I actually had a different question, not a difficult one. So I think it's a very nice overview, very clear. What I was wondering is, what do you expect? How different can the different nodes be? So I could imagine that there should be some basic, let's say, infrastructure in every node for you to be able to deploy the training and then collect data back. So how do you deal with that? So what do you do if we have to have one node over in Nijmegen and we have one in Linköping? How do you take care that you can train on both places? So what do you need from the IT, from infrastructure? And how can you unify it, or at least, well, get this to work?
Yeah, that's a good question. And I think that this comes down a little bit to the question we call alliance governance. So like I mentioned, you have this, when you have different hardware, there will be some, heterogeneity in the hardware, in the system. And that is okay if it's not too much. But I would say that I would recommend in a situation like that you try to formulate some sort of SLA between yourself, that maybe you should be able to compute an update in a certain time window, for example, and that you try to achieve that on all the sites. But other than that, there's no need for the hardware to be the same or the situation the same. Of course, there needs to be a common data preparation pipeline, so that you actually train on the same thing, roughly. But there can be statistical heterogeneity. I don't know if that answers your question.
Yeah, I'm thinking so. The speed is one thing, of course, but I could imagine, the data, software, yeah, everything could be different, right? Even the format of the data in different sources. You need to take care that you have the same kind of images and the same kind of annotations.
Yeah.
Which is not trivial, of course.
No.
But I think it's sort of this comes down to any type of I don't think this is specific to federated machine learning. If you would pool them in one location and try to do it the sort of traditional way, while you still have these same challenges. So it's sort of, I don't think it's I guess the problem that you have in federated machine learning is that maybe sometimes you are not aware of these differences. It's not very clear if you're unable to sort of, so it's sort of, there's uncertainty in these things. And I think that sort of, for example, if you work in a pre-competitive manner where you definitely don't want to share anything with others and so on, I mean, you have to sort of you have to agree on certain standards, and then at some stage, I mean, that it also comes down to how do you validate the model in that sense. How can I validate that it sort of got better from a federated? I mean, if it doesn't get better from using a federated model, well, I will just continue with my own data in that sense. So it's sort of well, there's different aspects of it, I think. But you're absolutely right that, I mean, it's sort of, you need to sort of agree. But many of these things are at least, I mean, what the format of images and so on, if that's what you're doing. I mean, that's usually relatively easy to sort of agree upon. Whereas other sort of heterogeneity might be more difficult to sort of accommodate for.
I will interject.
Say one more thing in that sense also. If you deploy systems on different infrastructures, I think it's important also that you have a system that is sort of infrastructure agnostic in that sense, and that, for example, if you have different type of resources, and I think that we have put a lot of effort also in, for example, in Scale in the Federated solution, that it is infrastructure agnostic, and you can run it on different types of cloud or on-prem hardware and so on. I think that's a very important point to make.
So I will make yes, Andreas.
Oh, sorry, you can actually see a little bit the sort of system heterogeneity in this plot here, the one we're talking about. Now this is a scaled down example so that we can actually run it on CPU or normal VMs. But here I'm running on my laptop, and then I'm running on a high-end VM in Amazon. So you see there is of course a distribution in the client update times when I do this computation. And this you would see on a, greater scale if you do this on data center level. Yeah, sorry, Joel, I just wanted to comment.
Yes, we have more questions in the pipe. Yes. I will just interject that a question that Jeroen brings up, we are trying to address that in the metadata task force in Bigpicture, where we try to harmonize standards and validators and converters and all this to ensure that we have data that actually possible to train on. The next question came on chat, and it's from Darren Trenner from Leeds, and a friend of mine in CMIV in Linköping. He says, great talk and a great first Bigpicture webinar. What computational needs are required at each node? I'm assuming that the model training at each node is quite computationally expensive.
Ola, do you want to answer that?
I'll just give you a bit of context as well. It's quite difficult to put scanners and machines into hospitals. The hospital IT departments can be a challenge. So I'm assuming that we need to put in a powerful GPU machine in each node for this. Is this correct?
Yeah, I mean, it's sort of in principle you need adequate infrastructure so that you can do local training. That sort of, and if you have less capacity, well, your computations will take longer time in that sense. So it's sort of.
Thank you very much. Yes.
I don't think I can answer it more than that. That sort of, it will definitely affect. But yes, since you are doing local training on that, so it's sort of that you will never get away from that.
Thank you.
So we have another question from another Joel, who is not me, but he's working in hospital IT. Joel Pettersson.
Thank you. Thank you for a very interesting topic. And I would like to ask if how do you address problems with data poisoning from malicious actors, and what kind of impact does a few bad actors have on the global model, so to speak?
That's a very good question, and it's also, of course, like an active area of research. And I think it's really hard to answer in full generality. So there are, but many of those are not production ready, I would say, but you could try different ways, like anomaly detection ways to detect this. One thing that is quite nice about this federated averaging scheme when you work with neural networks is that at least if these are transient, there is a chance that they are washed away. But I think and coming back to alliance governance again, I think maybe realistically, you would want to have a little bit of trust between at least if you work with medical data like this. But you have, of course, the malicious data poisoning. I mean, that's a very serious question. But you can, of course, also have data quality issues. And there are limiter schemes that you can apply on this aggregation level to make it so that like large unusual updates would have a lower impact on the global model. And this could be quite useful in this case. You get more robust, like that no bad client or update would completely destroy the global model. But this is a big area of research, and I think it's not extremely different. It's not that different in the federated setting from the centralized setting. This is about adversarial machine learning. maybe that the federated setting becomes a little bit more robust in some sense, because you have the possibility to wash away things.
I think
one challenge with these neural networks is that maybe you can't really, it's not easy to slice out bad contributions, but there we are working with things in my lab that will enable us to do that in different settings.
So I can see that we have one question from Georgios, if we can make it fast because we're running out of time.
Yes, sure. Thank you. Thank you, Joel. I'll make it very fast. So I also used to be a medical image analysis expert, but mainly working for MRI and PET, and I see this with great enthusiasm. It's amazing talks and presentations. Actually, I'm going fastly to my question. To what degree these models become semi-supervised from supervised? That was my main question in the context of federated learning.
So I don't think that we have done much on this topic. So I think that's.
We're actually looking for a master thesis student to work on it right now. So it's a very good question. I don't have a super good answer right now, but in a few months maybe.
I would be happy to discuss in the next steps.
Yeah, that would be amazing. Just reach out.
Thank you. Thank you very much, Andreas and Ola.
Yep.
Super. I see that we are sort of running out of time, and I've promised to leave a few minutes to Rick, who may want to say a few words on the rest of this seminar series. But as for me, as being the host for this seminar, I'll thank you for your time, and thank you, Ola, and thank you, Andreas. This has been very inspiring. I'll save all my questions for later when I see you at some other time. Rick, do we still have you with us?
Yes, I'm still here. So likewise, I would like to thank our speakers for today, and also Joel for hosting and proposing this seminar, which was a great kickoff, I think. So I would like to invite you all to also come up with suggestions for new seminars. We would like to schedule one every month. Preferably on, of course, on topics that we're working on in the project or that are very much of interest for many people in the project. So please reach out to us through the project management office email address. And we have scheduled the next one already for November 12th, I believe, which is on quite a different topic, but it's also very relevant for the project, and that is on the European Health Data Space Regulation. So basically on the legislation that will hopefully allow us to do all these cool AI, to develop more AI tools and allows us to get better access to data. Let's hope. So this will be hosted by Jos Dumontier and Magdalena from TimeLex, our partners in Work Package 5 and 3 who are working on this. So you're all very much invited to join that webinar next month. And I think with that, it's 4 o'clock, at least here in Utrecht. So I'd like to thank you all for joining, and I hope to see you next time again.
Thank you. Thank you so much. See ya.